So 15 train cars are connected in a row. Alrighty. So here's 15 cars. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Alrighty. And they are all 0.2 kilograms. And there's a coupler between each of the cars. And I pull on one side with 3 newtons of force. So I am not going to do 15 of these. I don't have to. As I said to you guys, there are shortcuts, and you should have seen them while we were doing it. This is going to be treated as 1 15 times 0.2 box. So 15 cars times 0.2 kilograms, suggesting it has a mass of 3 kilograms, the entire thing. So net force equals MA. 3 newtons equals 3 kilograms times A. The acceleration is 1 meter per second squared. So that's the acceleration of the system. I don't know what you guys are doing. A bunch of you got 1, but a bunch of you got some, not this. All right, so I want the coupling in the last car. Well, the last car is experiencing an acceleration of 1 meter per second squared, just like all the cars are. And it's experiencing a tension force this way, 2 newtons of weight downwards, a normal force upwards. So net force equals MA. So that'll be tension equals 0.2 times A. So the tension is 0.2 newtons. All right. I now need the tension in the acting on the 7th car. So I assume counting from the front, 1, 2, 3, 4, 5, 6, 7. So I'm not sure which tension they're talking about, so we'll find them both. Let's start with finding the tension on the lead side of the car. If I find the tension on the lead side of the car, that coupling right here has to pull 9 cars behind it. So 9 times 0.2 equals 1.8 kilograms. So again, net force equals MA, tension equals M, 1.8 times A, 1, or 1.8 newtons. So that must be the tension on the lead side of the 7th car. So now let's find the tension on the trailing side of the 7th car. Let's see. The trailing side, there would be 8 cars. So 8 times 0.2 equals 1.6 kilograms. Net force equals MA, tension equals 1.6 times 1, or tension equals 1.6 newtons. I'm not sure which answer they're really going for, but if we consider that the car has two tensions acting on it, the tension in this direction is 1.8 newtons, and the tension in this direction is 1.6 newtons. And that's for car number 7. We just figured out how much each coupler has to pull behind it. I've been trying to show you the whole time that when you do this, you end up getting the mass of all of the cars somewhere in your problem. I see no reason to do all 15 free body diagrams. 3 boxes lie on the ground. They're going to experience a force that will move them. There's a 5, a 15, and a 10. So 5, 15, a 10. Version 1 of this question, there's no friction, and the first box is experiencing a pushing force of 30 newtons. All right. We could use the shortcut from before, but we're going to be finding the normal forces anyways between them, so we'll just do the problem. There's only 3. Box number 1, the 5 kilogram box, is experiencing a pushing force of 30 newtons. It's also got its own weight, 50 newtons, and a normal force this way. But there's also a normal force between these 2 boxes, so it must be experiencing a pushing force backwards. I'll call that normal force 1. The 15 kilogram box is experiencing a Newton's third law normal force 1 in the forward direction. That is the force between these 2 boxes. It's also experiencing a downward force, 150 newtons, and an upward force, N. And it's experiencing a force between these 2 boxes, which I'll call N2. The last box, the 10 kilogram box, is experiencing N2 and 100 Newton force downwards, normal force upwards. All right, free body diagrams. Not drawn particularly well, but I think the system's going to accelerate. There's no friction, so I think the net force is going to equal MA. I'm going to make this way the positive direction. These are all those little things that you'll forget to do on the test, and you'll get you into trouble. Let's go with the first box. The 5 kilogram box is going to be 30 minus N1 equals 5A. The next box is going to be N1 minus N2 equals 15A. And the last box is going to be just N2 equals 10A. Any questions? Alrighty. Well, don't do that. So N2 equals 10. Let's put them all together right there. You can add them all up. The N1s will cancel and the N2s will cancel. And I'll be left with 30 equals 5 plus 15 plus 10 times A. Again, the one applied force, sum of all the masses, those add up to be 30, so it looks like A is equal to 1 meter per second squared. Now, it actually didn't ask for this, it asked for the normal forces between the boxes, but we needed to get someplace to get that, and acceleration seemed like the right way to go. If I plug this back in here, though, I can find that N2 equals 10 newtons. And once I know N2, I can plug it in here and find that N1 minus 10 equals 15, or N1 equals 25 newtons. So I took the acceleration and just plugged it back in to figure out what the other normal forces were. Not terrible. Now you're supposed to redo this problem with the applied force on the other side of the boxes. That doesn't really change very much here, but I don't know, if you want, we'll do it. Let's see, it means that this one's going to have 30 newtons in this direction. Again, we're taking this 30 Newton force and moving it to the other side. That's going to switch these around a little bit, but not much. I'm going to have N2 this way, just like before. I'm still going to have an N2 in this direction, but I think it's going to be bigger this time. So I'll draw it a little bit bigger. And there'll be an N1 back this way, just like there was before. And now on that first box, we'll just have a little N1 there. I'm going to switch what direction I call positive as well, because I think the system's going to go in the other direction now. So we'll make this the positive direction. Like I said, it doesn't change very much, but I'll have, let's see, I'll just write them all to the side. This one first, N1 equals 5A. Now this one, N2 minus N1 equals 15A. Now this one, 30 minus N2 equals 10A. But the acceleration is still 1 meter per second squared. That's not going to change. The box's masses are all the same and the force is the same. So I don't even have to add these together. I can just find right away that N1 equals 5 times 1, or 5 newtons. And I don't know, we can just do this one. 30 minus N2 equals 10 times 1. So looks like N2 is equal to 20 newtons. All right. So it said in the problem that M1 is greater than M2. So I think we're going to have a system that is going to accelerate this way. Now, we're asked for the tension in the cable holding the pulley. We want this tension. We'll call this tension in the pulley. I bet that would be equal to whatever the two downward tensions are here on the pulley, because the pulley doesn't go anywhere, so its net force is 0. So if I can find the tension in the cable, I just need to double it. Now I'm going to do this problem all the way with the kind of algebra that I think you should be able to do. You'll balk at it a little bit, but it's algebra that you've learned, and you won't maybe understand why I'm going to do all the algebra until we get to the end. And even then, I'm not sure some of you will understand, but some of you will, so it's worth doing it for you guys. I'm going to go ahead and establish that this direction is positive for this side, and this direction is positive for that side. I'll have a M1G downwards and a tension upwards. I will have the same size tension upwards here because the pulley is massless, and there'll be an M2G down, and I would draw it in such a way to make the net forces still work out so this thing goes in the right direction, but also the tensions are equal. So you're trying for both of those. The system accelerates, so M1G minus tension equals M1A, and tension minus M2G equals M2A. That's all you have to do for Newton's laws. We want the tension, but I think it's actually easier to eliminate tension first and find acceleration. So we'll do that first. I'll add these two equations and I'll get M1G minus M2G equals M1 plus M2 times A. We've done this already a couple of times. So A equals M1G minus M2G divided by M1 plus M2. So I now need to come up with the tension. So I need to plug this back in to one of these to get the tension. I think the bottom one's easier because the tension's already positive. So I'm going to do that one. So tension minus M2G equals M2 times all of this. So that's M1G minus M2G over M1 plus M2. Now you're supposed to get this for tension, so I would just add M2G to both sides. And this looks pretty crazy. And it's hard to make heads or tails of it. So since you guys are not really contributing very much, I'll give you a few minutes to add those two things together. You guys know things. You know that you can get common denominators and add the two fractions together. So do so. I'll give you a hint. Factor out the G. So you'll get M2 plus I factored out the G and I distributed the M2. So now get common denominators and add the two fractions together. This is within your wheelhouse. This is just algebra 2. I'll call on one of you in a minute, because this reduces down to something not too terrible. Need common denominator. So the way to get a common denominator is to take the M2 and multiply top and bottom by the denominator of the other fraction. It's no different than saying if I want to add let's say 3 to 2/3. Well, I'd have to get a common denominator. So I would multiply the 3 by 3/3 first to get common denominators, which would make it 9/3. So I'm just going to do that metaphorically over here. So M2 times M1 plus M2 divided by M1 plus M2. Just common denominators. I can distribute the M2 here and put it all under one fraction. So I will do that. So just one M1 plus M2. The left side of this will be M2 times M1 plus M2 squared. That's all of this. The right side's already been distributed, so plus M2 M1 minus M2 squared. Can you combine like terms? I expect you to. So I notice I have a positive one of these and a negative one of these. So when I combine those like terms, they turn to 0. And I have M2M1 and M2M1. So I have 2 of them. So the top will be 2 M2M1 over M1 plus M2 times G. This is the tension in the cable. Now, if M1 equaled M2, if that were true, if M1 equaled M2, the tension in the cable should be obvious. If M1 equals M2, does the system accelerate? You all understand that? If I put the same mass on both sides, it doesn't go anywhere? So consider what happens if M1 equals M2. It means both masses are the same. Right? Won't the top there be 2m squared and the bottom will be just 2m? The 2's cancel. One of the m's cancels. And I get just mg. The tension in the cable is how much each box weighs. That's because they don't go anywhere. What might not be evident to you is that this is clearly a weird kind of result. So here's what I want you guys to do. There's one of these on either side of the pulley, right? If we look back at the original picture, there's one on either side of the pulley. Assume M1 is 10 and M2 is 5. Right? I said M1 is greater than M2. I want you to find T for the pulley, which is 2 times the tension. Find it. Like, plug in the numbers to get the tension down there. So again, M2 equals 5, M1 equals 10. I may not be able to expect you to do all of this algebra, but I can expect that out of one of you. And remember, I want the total on the pulley, which is 2 times the tension. 130, or let's just go 131 newtons. What's the total weight of the 2 boxes? No, it's the mass. What's the total weight of the 2 boxes? So, well, if we're using 10 for G, which is what I think, did you use 9.8 for this, or did you use 10 for that? 9.8. Okay. So that would be 147, right? We hung 147 newtons of weight on either side of the pulley, but the pulley only pulls up with 131 newtons of weight, or 131 newtons of force. Why? Do you see a discrepancy here? If not, Thursday's test is going to be tough for you. But you should have a problem with this, or be able to explain why in this problem, this is 147 newtons pulling downwards, but this is only 130 newtons pulling upwards. Why aren't they the same? I mean, it's clearly an unbalanced force, isn't it? This is why you guys are going to have trouble. And this is how you answer question A. What's happening to this box? It's accelerating downwards. And what's happening to this box? is it clear that more weight is accelerating downwards than is accelerating upwards? So the truth is, the weight of this system is accelerating downwards, right? A bigger box is going down at the same speed as a smaller box is going up. So the average weight of the system is accelerating downwards. In fact, the net force on the system would equal the mass of the system times A. This is not the acceleration of one box. This is the system. The net force is 147 minus 130 equals 15 times A. This is the average acceleration of the center of the system, which is accelerating downwards. Mostly what I want you to see is that unless these two things are the same mass, they will accelerate. And the ceiling doesn't pull up with the full weight of the system because the system is falling to the ground. Yes, a small part is accelerating upwards, but the big part is falling to the ground. Everybody see that okay? I want you to. It's important to me. Important enough for me to spend, 14 minutes on it. So if I was to drop you near the surface of the earth, which is the same as pitching you off the balcony, gravity would apply a force to you and pull you downwards. Now, you know a little bit about this. For example, you know that you could figure out what your weight is. It's going to equal mg, right? Now, you guys are all different weights, but let's just assume that you're somewhere between 120, 160 pounds in this room. So that's around 60 to 70 kilograms. So let's just say 60 kilograms for right now, okay? What would be the weight of a 60 kilogram person? I mean, if you use G as 10, it's one number. If you use G as 9.8, it's another. Do you care which one we use? So 600 newtons. By Newton's third law, the Earth is also experiencing an upward force of 600 newtons as you fall. So the real question would be, are you falling towards the Earth or is the Earth falling towards you? And I don't ask this like in some philosophical, stupid way. I'm asking it for real. Which one of you is actually moving, you or the Earth? Now, we know that your acceleration is 10 meters per second squared. That's the acceleration you experience. It comes directly from net force equals ma, and we know the acceleration due to gravity because we've done experiments on it. That's not what the Earth is doing. The Earth is experiencing this 600 newtons of force from you. So if we want to know what the Earth is doing, we would need the mass of the Earth, and we'd have to determine the Earth's acceleration due to falling towards you, your gravity on the Earth. The mass of the Earth is 5.97 times 10 to the 24th kilograms. And you're applying 600 newtons of force to it. So one of you carefully use your... So if you've done this, can somebody give me the acceleration?
1.005.
Yeah.
Pardon the interruption. Today is a makeup green...
Is the effectiveness of a force. Both you and the Earth experience the same force, but it's more effective at moving you. You have less inertia. So this wasn't a philosophical question. It's a measurement question. The Earth doesn't move because you fall. I know a lot of you think the Earth revolves around you, but it clearly does not. Right. Number 2, consider just the first 2 boxes from the above question, the 5 and 15 kilogram boxes. They now have a coefficient of kinetic friction of 0.3 between the floor and the box. Calculate the normal force between the two boxes if they are pushed at a constant velocity. Alrighty. So, does it matter to you which side we put this force on? I mean, it does change the problem. It makes the force bigger on one side than the other. I mean, you should know which side it would be bigger on. If you push on a small box, it makes the normal force bigger. Push on the big box, it makes the normal force smaller. So, but which side do you want me to push the force on, Aaron? Left or right? Okie doke. So we are applying a force here. We don't know how big this force is. We know that this box is 5 kilograms and this box is 15 kilograms. We do know that the net force on the system will be 0 because it says the boxes move at a constant velocity. All right. But it does say there's a coefficient of kinetic friction of 0.3 between the floor and the boxes. So let's start with the left box. It's experiencing weight downwards. I think that'll be 50 newtons. It's experiencing a normal force upwards. It's got this applied force to the right. And there's clearly a frictional force, but there's also a normal force. Those are all the forces I think that act on the 5 kilogram box. Any question about any of those? Excellent. I'm going to go on to the next box. It's got weight, 150 newtons, normal force. There's got to be a sideways normal force this way too. Maybe we'll put NX and say that's a normal force in the X direction. But it's also experiencing a frictional force. Those two frictional forces aren't the same. So we need to say maybe friction on the 15 and friction on the 5. Okay? All right, so we know the net force is 0. So this one, NX minus the frictional force equals 0. The other box, FA minus NX minus the frictional force equals 0. Any question about those choices? Now, we can do more because we know that kinetic friction is equal to mu times the normal force. And in both of these situations, the net force in the y direction is also 0. So for the box on the right, normal force minus 150 equals 0. And the box on the left, normal force minus 50 equals 0. We following along okay? Now, there's more things to do here, like, all right, well, normal equals 50 and friction equals mu times the normal force. You see what I've done? I've just combined the things together. Here, normal equals 150 and friction equals mu times the normal force. Still doing all right? So let's put all these things together. NX minus 45 equals 0. So the normal force between the box must be 45 newtons. On the other side, FA minus 45, because the normal force in the x direction is 45, minus 15 equals 0. Well, look at that. That means the applied force was 60 newtons all along. So I don't have to do the other part of the problem. That was the answer. Go ahead, Aaron.
Sorry, where's the 45 coming from and then smaller?
Well, Nx is a Newton's third law force. You see what I'm saying?
Yeah.
So when we found Nx here, I just used it up there. And that's why I put it down here. Oh, okay.
So the normal force doesn't change, like NX doesn't change between boxes?
Well, no, because remember, what we have here is there's a force that's acting on this box this way, Nx. That's because these two boxes are in contact. There's an equal and opposite force acting on Nx in this direction. By Newton's third law, those two normal forces have to be equal but opposite. That's why the one was negative in the one equation and positive in the other, but they're the same size. Is that okay?
Yeah.
Excellent. Excellent. Good question. Are we pretty good with this one? All righty. Yes? You think you...
I think I have one question about the NX.
Okay.
For the NX, we solved it on that side,
Mm-hmm.
but I'm confused on the front side. There's like two NX, is it NX and NX, so why did you use this one? Do you know what I mean?
Okay. If we... Let me get all these little arrows out of the way. In trying to solve the problem, let's get the answers out of the way, okay? If we back up to here, to this moment, so just looking at when we started here, this was right here, this was us saying the net force in the x direction equals 0. And you understood where those two forces came from, right? And here was also, on the other box, net force in the x direction equals 0. Now, separately, we can figure out the size of these two frictional forces. Those two frictional forces depend on these normal forces. Well, on this side, the normal force equaled 150 newtons because it's balancing the weight of the box. Right? That's from saying net force in the y direction equals 0. That good?
Yeah.
Okay. But we also know friction equals mu times the normal force. So we just said friction equals 0.3, because that's mu. And the normal force here was 150. And that gave me a frictional force of 45 newtons. Okay? Set that aside for a minute, all right? Over here, this normal force, it has to equal 50. Right? Balancing up and down, net force in the y direction. So this frictional force has to be equal to mu times that normal force of 50. That frictional force is 15 newtons. All good? All right. Well, we were asked to find the normal force between the boxes. Can't use this to find it because I don't know what that force is. I could use this to find it because I do know what that force is. Right, so I went, all right, let's look at this side. Since this side can be solved, let's find what that normal force is. And we could have stopped there because the problem just wanted the normal force between the boxes. But I said to myself, look, we're working it out. We could find out what this applied force is too. That was actually not asked in the problem. But if I had wanted to find the normal force and I was looking at this equation, I wouldn't be able to use it because I don't know how hard I pushed on the boxes. I could have put the 15 in there that we found just a second ago, but that still wouldn't be enough for me to figure out what this force is without knowing this force. Does that make sense?
Yeah.
Okay. 15 toy rail car question. So 15 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 15 cars. And we are pulling to the side with, what was it? 2 newtons of force, 3 newtons of force? How much force were we applying to the cars? Number 3. So 3 newton force. So 3 newtons. And each car is 0.2 kilograms, right? All right. Any friction in this problem? It says very little, so no friction. That's the sign of no friction. So, first thing I'm going to do is find the acceleration of the system. I am not drawing 15 free body diagrams. What I am drawing is one big train car that has a mass of 15 times 0.2, which is going to be 3 kilograms. Is that right? So, net force on the system has to equal the mass of the system times A. The only force acting on the system, since there's no friction, is 3 newtons. That has to equal 3 kilograms times A. So the acceleration is 1 meter per second squared. Any question about what I did there? All righty. The truth is, though, every one of these cars is accelerating at 1 meter per second squared, including the last car. Now I'll draw a free body diagram. The last car is experiencing a tension this way, weight downwards, and a normal force upwards. Net force on the last car equals M, 0.2, times A, 1. So the net force is 0.2 newtons. That is from the tension, the only thing pulling on the car to the right. Right? One little car, that one. All good? Any questions about that? All right, so now they're asking about car number 7. They want the tension in car number 7. Let's go put this stuff over there. I don't need it anymore. So car number 7, let's see. Where is that guy? 1, 2, 3, 4, 5, 6, 7. Seems to me that there's 2 tensions acting on car number 7, right? One going forwards and one going backwards. So let's figure out the one going forwards first. How many cars is that? How many cars are being pulled by this one coupling device? Looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them are. All good? Well, that means 9 times 0.2 is 1.8 kilograms worth of cars. So there is a tension in this direction on that whole block of cars. Net force equals MA. So tension equals 1.8 times A. They are all accelerating at 1 meter per second squared. So the forward tension is 1.8 newtons. All good? Well, we now need to find the tension on the backside of car number 7. How many cars are behind car number 7? 6? 8, I think. 1, 2, 3, 4, 5, 6, 7, 8. 8 cars are behind car number 7. They have a mass of 8 times 0.2 kilograms, or 1.6 kilograms. So the tension that acts on those rear 6 cars, net force equals MA, tension equals 1.6 times 1, or 1.6 newtons. So, car number 7 has a tension this way of 1.8 newtons and a tension this way of 1.6 newtons. Those are the two tensions that act on car number 7. Now, yeah, we could have made a free body diagram for all 15 cars. Boy, I'm glad we didn't do that. Could you imagine T1, T2, T3, T4, T5, T6, T7? No, thank you. I think this is a better way to do it. This question's tough, actually. It's pretty challenging. So I would forgive you if you had trouble or had any idea. You can't do part A because we didn't talk about center of mass.
Oh.
What? Well, the string or a bar or something, I don't know. Do you want me to make it look like a string? I can. And I've got pulleys, so you kind of see what we're going with. So we're going to put numbers to it. We're going to say on this side, we've got a box that is, let's use easy numbers. Let's go 5 kilograms. And this side, a box that's 10 kilograms. That okay? And we're also going to state that T with a P on it means the tension on the pulley. Everybody okay so far? Tension on the pulley is upwards, and there are 2 tensions downwards on the pulley. They're the string. Right? So this is pulling up, but 2T is pulling down. Everybody all okay so far? All right. Now, we know that this is going to be 100 newtons minus tension equals 10A. We're going to assume the system's going that way. That all makes sense? The other side, tension minus 50 equals 5A, because this side is going up. Still good? I want to find the tension, but I think the only way to do so is to find the acceleration first. So I'm going to add these two together, and I'll get 100 minus 50 on the left side, and 5 plus 10 times A on the right side. We still doing okay? So 50 equals 15A, or A equals 50 divided by 15, which is 10/3 or 3.3 meters per second squared. I think that's right.
Did the 50 also have newtons? 'Cause it would
Yeah, it's 50 newtons. Yeah. And then I just added them together. All right, so let's go back and get the tension now. We'll use this one to get the tension. Tension minus 50 equals 5 times 3.3. Everybody see where I got that? So tension is, let's see, 5 times I'm getting that the tension equals 67 newtons. Is that what you guys got? All right, so remember this one, 50 newtons. This one, 100 newtons. So 67 is in the middle, isn't it? Right?
Yes.
It's in the middle? All right. 2 times that tension, 2 times 67, is 133 newtons. Okay, now here's the thing. Here's the culminating thing. This is the thing I want you to realize. We have 150 total newtons of weight, right? But the string is only pulling up with 133 newtons of force. So the upward force that the pulley is pulling upwards with is less than the total weight of the system. Why? Because these generally are accelerating downwards. So the net force upwards is less than the weight of the system. Does that make sense? That's why we get 133. If you do it with M1 and M2, you get a monster mess of